Hi, this is Physics Echoes. We all do different types of measurements. I'm raising a question for students to ponder. Can scientists ever be truly certain of their discoveries? Scientists aim to achieve a true value of a quantity from their measurements. However, limited precision of the apparatus or devices used brings in some uncertainty. So, in order to do the analysis of data collected, uncertainty of devices need to be quantified. So what's this uncertainty? It is the range above and below a stated value over which any measurements would fall. The words errors and uncertainties are sometimes used to mean the same thing. This is true when referring to the experiment that have a known correct result, as the measurement differs from the true value is error. While taking measurements, how do these errors come in? It's either due to wrong technique or from the system. If the error is due to limitations of scale or wrong positioning of eyes while taking measurements, or unable to respond immediately while making observations that change quickly with time, like counting the oscillations, then we call it as random error, as it's unpredictable. To reduce random error, we repeat observations few times and then average the collected data. The error is due to wrong calibration or zero error, that is due to the instrument, then we call it as systematic error. Note here, repeating the experiment, averaging the data will not reduce systematic errors. So this diagram shows the zero offset error. How to identify these errors from the graph? Let's look at systematic error first. Graph of voltage versus current. The given graph is what is expected. That is, when the voltage is 0, the current should also be 0. You can see that. However, if the apparatus is not corrected for zero error, it will read either a higher or a lower value of current, leading to have a straight line of same gradient above or below the expected line. In short, the graph will have a y-intercept denoting systematic error when it is expected to pass through the origin, as shown in this example. If the data points are scattered around the expected line, like this, instead of falling on the line, then the error is random. So to gain better understanding, the errors have to be quantified. We take single measurement or resort to multiple trials depending on which the procedure of quantification changes. For single measurement, if analog instrument is used, then uncertainty equal to least count divided by 2. What is least count? This is the smallest possible measurement that can be taken by a given instrument. If digital instrument is used, then uncertainty will be equal to the least count, which is an indication of the fluctuating digit while taking measurements. For multiple measurements, like when we are performing the trials, uncertainty is equal to half the range. Or easier way to remember, maximum value minus minimum value divided by 2. Let's see how to incorporate these quantified uncertainties with measurements. Figure 1 shows the piece of paper being measured whose length is 23.2 centimeter. It's an analog device. Therefore, uncertainty will be equal to half the least count. In this case, it's 0.2 centimeter. Therefore, uncertainty will be 0.1 centimeter. That is, the least count is 0.2 centimeter. So, uncertainty will be 0.1 centimeter. This is what we call it as absolute uncertainty. How do I represent it? L equal to 23.2 plus or minus 0.1. L plus or minus delta L. This is how we represent it. Now, this is the measured quantity. So I can write this as measured quantity. And this is the absolute uncertainty. So, from this information that we have it right now, we can find what's the contribution of this uncertainty. That is, what fraction of measured value is the uncertainty, which we call it by the name fractional uncertainty. It's given by the equation absolute uncertainty, which is here, divided by the measured value. So absolute uncertainty divided by the measured value, which is 0.1 divided by 23.2 as per this example. Also, this helps us to determine the percentage uncertainty, which is the fractional uncertainty multiplied by 100. All right. So in order to check your understanding, try to find these quantities, that is absolute, fractional, and percentage for figure 2. Pause the video, write down the answer, and check. Since the least count is 0.1 centimeter for figure 2, absolute uncertainty will be 0.05 centimeter. If the error in both the sides are considered, that is here and here, then I can consider absolute uncertainty as 0.1 centimeter. Rest of the values are here. So what we discussed before is for individual measurements. While we do the experiments, data is collected for computing new quantities. Let's see how these errors are processed during mathematical operations. That is, for addition and subtraction, uncertainties, the absolute uncertainties of individual quantities are added, whereas while doing multiplication and division, we work with fractional uncertainties and percentage uncertainties. Remember, by adding uncertainties of measured quantities, corresponding uncertainty of calculated values are obtained. So let's look at an example. A rectangular box of dimensions are shown here. It's labeled as L1 and L2. In order to find the total length of two sides, we have to add L1 and L2. So let's see. What do we get? We add the measured quantities, giving me 11.60, and we add the absolute uncertainties, giving me 0.10 centimeter. Keep in your mind the decimal place for measured and absolute uncertainty should be the same. Moving on. If we want to find out how bigger is L1 compared to L2, then we need to subtract. However, absolute uncertainties will still be added. That's why still we have 0.10 centimeter. What's the reason behind this? The uncertainties will not be eliminated, or I say reduced, as one takes or as the experimenter takes two measurements. Whether I'm adding or subtracting, the uncertainties will be added up. Now, if we want to find the area of the rectangle, then it is a multiplication. Then we should work with fractional or percentage uncertainties. So let me show you how to work stepwise for multiplication and division. Step number 1 is write down the equation, which is here. Calculate the quantity, which is 32.64. Step number 2, write down the fractional uncertainty of each term and add the fractional uncertainty. So delta A by A equal delta L1 by L1 plus delta L2 by L2. Once we succeed in writing this, substitute the known values and add the fractional uncertainties. So what do we get? Delta A by 32.64 is equal to 0.05 over 6.80 plus 0.05 over 4.80. This is giving me, that is the right hand side is giving me a value 0.0177. From this, I can find out delta A as 0.0177 multiplied by A, which we found out here as 32.64. When you do that, you get 0.58. So we have propagated the error. Now, how to write the final answer? So we can write this as 32.64 plus or minus 0.58. However, the general rule is to express uncertainties to one significant figure. Therefore, the answer will be 32.64 plus or minus 0.6. It's not over, but the decimal place of uncertainty and measured quantity should be matching. So this I will rearrange it further to give 32.6 plus or minus 0.6 centimeter square. All right, centimeter square. You can do the same thing for division, and you should be getting an answer equal to 1.42 plus or minus 0.03. This is the answer for division. You can try this on your own. Now, when we look into our experiments, graphical analysis is of paramount importance. So, how to work on calculation of uncertainties of gradient and y-intercept of linear graphs. Velocity time graph is shown here. So, the first step is use the error bars and draw best fit, worst fit, and worst fit lines as shown here. I was about to say max fit and min fit, which is the same as the worst fit. Now, use the option display equation and then show the equation in the graph. Uncertainty in gradient is equal to maximum gradient minus minimum gradient divided by 2. So, these are the equation for the best fit line, the max line, and the min line. So, uncertainty in gradient will be equal to 2.2, which is here, minus 1.8, which is here, divided by 2, giving me 0.2. So, the gradient answer will be 2 plus or minus 0.2, or I will write more correctly as 2.0 plus or minus 0.2, because the decimal place of uncertainty should match with the decimal place of the measured quantity. Similar approach can be adopted to find the uncertainty in y-intercept. Maximum y-intercept minus minimum y-intercept divided by 2 will give you the uncertainty in y-intercept. I hope the video was helpful. For any doubts, contact physicscourse@gmail.com. That's all for today.